Hi, I'm Mark Barsamian. In this video, we'll be discussing the area between curves. This material is from section 6.1, just the first couple of pages of that section, and just the first couple of examples. The corresponding homework is this set of 9 exercises from section 6.1. Recall the concept of unsigned and signed area, which was first introduced in the video for homework 76. Back when we were discussing section 5.4, the definite integral. We discussed two kinds of area created by the graph of a function and the x-axis from some x equals a to x equals b. The two kinds of area were the unsigned area, which would be denoted 1 plus 2 plus 3 for these regions listed there. And then what was called the signed area, which would be 1 minus 2 plus 3. That is, regions under the x-axis get a negative sign. Back in chapter 5, in sections 5.4 and 5.5, we were primarily interested in signed area. We saw the development of the definite integral, which was defined as the limit of Riemann sums, and it refers to signed area. So this symbol, which denotes the definite integral, is that signed area. But now in chapter 6, we're interested in finding what is referred to as area between curves, which the convention is that it means unsigned area. So how are we to find unsigned area if our only tool for finding area is the definite integral, which finds signed area? Well, the key is to first define what I will call simple regions. Here's the definition. Suppose that top parentheses x and bottom parentheses x are continuous functions. This should say functions. And furthermore, suppose that the function called bottom has y values that are less than or equal to the y values on the function called top on some whole interval a comma b. So it would be a picture like this. Well, then the region bounded by those four curves, what I have shaded here, the four curves that are y equals top of x, y equals bottom of x, this vertical line x equals a, and this vertical line x equals b, that region is what we'll call a simple region. Simple because it has a clear top curve and a clear bottom curve and clear endpoints. This theorem explains how one can use the definite integral, which remember is about signed area. It explains how you can use the definite integral to find the unsigned area between curves for simple regions. And it goes like this. If top and bottom are continuous functions and bottom of x is less than or equal to top of x on that whole interval a comma b, then that region bounded by those four curves is what we call a simple region. And the area between curves, that is the unsigned area for this region, is given by this definite integral. You integrate the integrand top of x minus bottom of x from a to b. And again, that gives the unsigned area. For the rest of this video, we'll study examples involving computing the area between curves using that theorem. The first example is similar to two of your homework exercises. Function f of x has this graph shown. Question A says, set up a definite integral that represents the area between the graph of f and the x-axis from a to b. Now remember, this terminology means unsigned area. Well, if you look at our theorem, we have to identify a top function and a bottom function and our interval. Well, on this interval, the top function is clearly f of x. Well, and the bottom function is the function y equals 0. So that means the unsigned area is given by this integral. In the end, the unsigned area is given by the same integral that we would use to compute the signed area of that green region. That makes sense. That green region is above the x-axis, so we know that its signed area will be a positive number. So it makes sense that we would just use that integral to find the positive number that's the area of that green region. But it's useful to work with that theorem and get used to identifying the top and bottom functions, setting up the formula for this integral, and then seeing what unfolds. The reason is that in more advanced problems, it won't be so obvious at the beginning what we're supposed to do in terms of setting up the integral. So it will be helpful to have lots of practice setting up the integrals in very simple problems. Okay, question B. Set up a definite integral that represents the area between the graph of f and the x-axis from B to C. That's that region. Well, notice on that region, the top graph is y equals 0, and the bottom graph is f of x. We end up with the result that the unsigned area is the negative of this definite integral from b to c of f of x. Now let's go back up and look at the graph. That makes sense because if we integrate f of x from b to c, we would find the signed area of that blue region, which would be a negative quantity. So to turn that into a positive quantity, we would need to put a negative sign in front of that. So in this expression, this definite integral gives the signed area, which is negative. And then when I stick the minus sign in front, that turns the number into a positive number, which will be the unsigned area. Question C. Set up a definite integral that represents the area between the graph of f and the x-axis from a to d. That's all the way from a to d. Well, you see that I'll need three integrals. One is the integral from a to b, the other is the integral from b to c, and the third is the integral from c to d. On the green regions, the top graph is f of x. So those integrals will look just like this. The regular integral that would find the signed area of f of x. But on the middle interval, we've already seen that the integral needs to have a minus sign. So there's our definite integral. It's actually three definite integrals. And you can see that's the integral that we did in question A. It will turn out to be positive because f is above the axis. This is the integral that we know will be negative. This minus sign in front of it turns that quantity into a positive quantity. And then this integral we know will be a positive number because f of x is positive on that interval. That's the end of that example. Let's go on. Example 2. Find the area bounded by the graphs of y equals x squared minus 9 and y equals 0 over this interval. This is similar to one of your homework problems. Well, the key in all of these problems is to go back and look at the theorem and realize that you have to start by knowing the top and the bottom functions. And there's no way to do that without being able to visualize a graph. So we have to start by graphing our two functions. Let's first graph y equals x squared minus 9. We'll graph y equals x squared first. There are the famous points on the graph of y equals x squared. Now by transformations, we can graph y equals x squared minus 9. Now finally, we can visualize the region that we have in mind. The region bounded by that graph and y equals 0 over that interval. There's our region. You can see that on that region, the top graph is y equals 0. And the bottom graph is y equals x squared minus 9. So now we're ready to set up the integral. And there's our result. You see that the format that I used was the same format that I've always used for definite integral problems. I used the fundamental theorem of calculus to say that this definite integral was equal to this calculation involving an indefinite integral. Then I broke off the indefinite integral details off to the side and brought them back in. And notice that the final answer is a positive number, which is what we expected because we are trying to compute an unsigned area. Let's go on. Example 3. Find the area bounded by the graphs of y equals x cubed plus 7 and y equals 0 over the interval -4 to 2. Well, our approach has to be the same as it was in the previous example. We have to first figure out what the region looks like so that we can figure out the top graph and the bottom graph. So that will involve graphing this function. We'll graph it by transformations, just as we did in the previous problem. So there's the graph of y equals x cubed plus 7, obtained by transforming the graph of y equals x cubed by moving it up 7 units. You can see that over this interval, the top graph is y equals 0. The region that we're interested in is that blue shaded region, which is below the axis. Now we're ready to set up the integral. There's our result. The number positive 46 is our unsigned area. Notice that I did the indefinite integral just right in line. I didn't bother doing that indefinite integral off to the side because we've done enough of these now that you should be able to do these faster without having to break off the integral off to the side. Well, I mean, you should be able to follow my work when I do that. If you find that you still need to, certainly break this off to the side, do the indefinite integral details off to the side, and bring them back in. Certainly if that kind of organization helps. But for this problem, I just decided to do it right in line. Let's go on. Example 4. Find the area bounded by the graphs of y equals minus e to the minus x and y equals 0 over this interval. Give an exact answer and a decimal approximation. Well, we need to figure out the graph of y equals e to the minus x. We'll do that by doing two transformations of y equals e to the x. So there's our region. You can see that on this interval, the top graph is y equals 0, and the bottom graph is that function. With that information, we can set up the integral. There's our solution. Notice that the indefinite integral used a rule for integrals that comes up frequently, and it's useful to remember the rule along with its corresponding derivative rule. The rule is this. The derivative of e to the kx is k e to the kx, but the indefinite integral of e to the kx is e to the kx over k plus c. In this problem, we have k is -1. Notice that I went all the way to the end using symbols. I obtained this exact answer. That's the only way to write the answer exactly. Then I typed that into a calculator and rounded to 3 decimal places and got this decimal approximation. Remember, if you write down decimals as your answer, that's an approximation. Even if you write down 30 decimals or 300 decimals, it's an approximation. The only way to write the answer exactly is that. That's the end of that example. Let's go on. Example 4 says find the area bounded by the graph of y equals -5 over x and y equals 0 over this interval. Well, we have to graph that function using transformations. When I use transformations, that flips the graph over and multiplies the y values by 5. So we end up with this graph that's below the x-axis. So our region is there. Our top graph is y equals 0. And our bottom graph is this function. With that information, we can set up the integral. We'll do that on the next page. And there's our result. We get the number 5. Notice the indefinite integral of 5 over x is simplified by doing 5 times the indefinite integral of 1 over x, and using the indefinite integral rule for 1 over x, you get 5 times ln of absolute value of x plus c. Substitute that back in. The constant of integration cancels. And then we go to work simplifying the absolute value expressions. Absolute value of e is just e. Absolute value of 1 is just 1. And then we simplify these logarithm expressions. ln of e is just 1. ln of 1 is 0. That's the end of that example. We have one more example. Question 5. Find the area bounded by the graphs of this crazy function and y equals 0 over this interval. The solution is to first figure out what this graph looks like. Notice that it's a chunk of a circle. It's a circle radius 7 centered at 0, 0. If I solve that for y, I can get part way there. I have this plus or minus, but the formula that we are given is just the square root without the plus or minus. That means that we're looking at the top half of the circle. So there is our region. Notice that it's above the axis, and so the top graph is our y equals square root of 49 minus x squared. Now we can set up the integral. We don't have techniques for finding that definite integral. But wait a minute, we can just use geometry. Using geometry, we see that the area is a quarter circle, and we have the radius, so it's just simply 1/4 times pi times 7 squared. So we get this exact answer, which is 49 pi over 4. That's the only way to write the answer exactly. Rounded to 3 decimal places, we get this approximation. That's the end of that example, and that's the end of the video. Thank you.